Welcome to this video on simple harmonic motion, which is part of our modeling with differential equations topic. So if we've got a differential equation which is in this form, d2x by dt squared is equal to minus a constant times x, or we can write it like this, then what we find is that models the motion of a particle going backwards and forwards repeatedly. It's called simple harmonic motion, and not surprisingly, we end up with a solution in terms of trig functions. If you think of the graph of sine of x or cosine of x, the way this works is that the value on the y-axis is the displacement from the center of the motion. So let's look at an example. Solve the differential equation d2x by dt squared plus 4x equals 0. Well, we're going to write out our auxiliary equation. Auxiliary equation is just m squared plus 4 equals 0, and the solutions to that are m is equal to plus or minus 2i. So the general solution to our differential equation is x is equal to a cos of 2t plus b sine of 2t. Now remember that when we have complex solutions to the auxiliary equation, we normally have e to the power of the real part of this times t outside a bracket, and then the trig part inside it. But here the real part is 0, e to the 0 is 1, so we can just miss that out here. We've got some values to substitute in to find the values of a and b. So at x is equal to 4 and t is equal to 0, we've just got 4 is equal to a times cos of 0 is 1 plus b times 0, so a is equal to 4. And at x is equal to minus 4, x is equal to minus 4 when t equals pi over 4. So we've got minus 4 is equal to a times cos of pi over 2, a cos pi over 2 plus b sine pi over 2. Well, cos of pi over 2 is just 0, so this is, and sine of pi over 2 is 1, so we've got minus 4 is equal to b. So b is equal to minus 4. So our particular solution is x is equal to 4 cos of 2t minus 4 sine of 2t. Now, usually we leave solutions in this form, but of course we've seen functions like this before in the single maths course, and one of the ways we could rewrite this is in terms of r and alpha. So we could rewrite it like this, equivalent to x equals, we get 4 root 2, so that's just 4 squared plus the negative 4 squared. Square root of that is 4 root 2 times cos of 2t plus, it turns out to be pi over 4. I'm not going to go through the working for that, but you might like to check that you can do that. one of the advantages for writing this in this form is that we can see the furthest displacement away from the center of the motion, that is the amplitude, is going to be this 4√2. So amplitude of the motion equals 4√2, or if we want to write that in as a decimal, which might make more sense if we've got it in meters or some other units, we've got 5.66. 5.66. And then we also talk about the period of motion, and that is basically the time it takes for this particle to go through one whole cycle. So if it starts in the center, to go out to its furthest point this way, out to its furthest point this way, and then back to the center. And the way we find that is we're going to say the period, well, 2t, because that's what's changing here, has got to be equal to 2 pi radians. So then t is equal to pi, which is 3.14, and here we would have it in seconds. I should probably put meters here. So that's our first example of simple harmonic motion. Let's go on and have a look at the second example. So the second example here over the page, we've got a particle P attached to the ends of two identical elastic strings, and the free ends of the springs are attached to 2 points A and B. So if we have A here and B over here, what we've got is we've got a spring which we quite often sketch like this. We've got another spring here. There we go. My artistic skills not awfully good here. And then we've got our particle here at point C. And then the particle is going to be pulled and released, and these two springs are going to mean that it goes backwards and forwards here. So the subsequent motion of the particle can be described by this differential equation. Remember that x double dot means d2x by dt squared. This is a notation that we use when we're differentiating with respect to time. So part A, describe the motion of the particle. We're going to say the particle oscillates about a fixed point. Now here I've drawn C in the center. I think actually I should have drawn C one side or the other. It says it's held at C and then it will then it's released. If it's held in the center, it won't move. So that fixed point won't necessarily be C. C is the starting point here. And we could also say it moves with simple harmonic motion. Okay, so part B says solve the differential equation to find x as a function of t. So we've got x double dot equals minus 25t. So our auxiliary equation is actually let's just rewrite this, x double dot plus 25t equals 0. Auxiliary equation is m squared plus 25 equals 0. So m is plus or minus 5i. So we've got x is equal to a cos of 5t plus b sine of 5t. And we've got some initial values, not just for x, but also for the velocity. So what we'll do is we'll just differentiate this so that we've got v, which is equal to x dot, is minus 5a sine of 5t plus 5b cos of 5t. Now we're going to substitute in our values. So t equals 0. We've got x is 0.4. So 0.4 is equal to cos of 0 is 1. So a plus 0. So a is equal to 0.4. And then we've also got velocity v equals 0 when t equals 0. So we've got 0 is equal to well, sine of 0 again is 0. So we've got minus 5a times 0 plus 5b times 1. Cos of 0 is 1. So b is equal to 0. So our particular solution is x is equal to 0.4 cos of 5t. And we also have v is equal to minus 2 sine of 5t. Part C, state the period of the motion and calculate the maximum speed of P. Well, for C, period, well, we're going to write T, 5T is equal to 2 pi, so T is equal to 2 pi over 5, which is 1.26 seconds. And maximum speed remember, speed is the magnitude of velocity. Magnitude of this velocity is going to go, well, down to minus 2 and up to 2. So maximum speed is 2 meters per second. Okay, so that's it for this introduction to simple harmonic motion. There are questions on simple harmonic motion in exercise 8b in the textbook, and what we'll go on to next is to look at what happens in reality where in situations where particles move with simple harmonic motion. Usually there's some factor which is slowing them down. It might be friction, it might be air resistance. And so we look at the damping effect of that on the motion. Okay, thank you for listening to this. Thank you for watching, and we'll finish there.